So a solution is considered are considered solutions. Which of these would be considered solutions? Okay, do we think the Windex is a solution? Yep. Right, there's not chunks of anything floating around in it, right? It's the same throughout, and it's a mixture of some things. Okay, what else is a mixture? The oil. What else? I would agree. Anything else considered a solution? Why isn't water considered a solution right here? It's pure. There's nothing mixed into it, right? And would we consider tap water a solution? I think so, because there's minerals and other like things, additives in that tap water. But if we're talking about pure H2O, right, that's considered just a pure substance. It's not a mixture. And then what's happening here with the grass? Okay, yes. Yeah, it's not a mixture. There's nothing that's dispersed throughout it evenly. Okay, so no, I would not consider that a solution. What would be another type? Listen. What would be another type of mixture? A heterogeneous mixture, good. And what are examples of heterogeneous mixtures?
Fruit salad.
Fruit salad, yes. Agreed. Anything that we can distinctly pick out the parts of it. Okay. Spoiled milk, yes. Cereal, coin jar, right? Those are all examples of trail mix, homogeneous mixtures. We can pick out the distinct parts. What about when you leave Kool-Aid in the fridge for too long? What happens?
It starts to like uncool.
It starts to un-Kool-Aid. Yes, I would agree with that. What happens? It settles to the bottom, right? It starts to separate. That would become a homogeneous mixture. But then how can I fix it? Shake it, stir it, right? I can make that switch again and make it be, it becomes heterogeneous. I can mix it again to be a homogeneous mixture.
Oil and water be one?
It would be heterogeneous because they stay on separate levels. Yep, I can pick out the distinct parts. Homogeneous mixture. Okay, and a homogeneous mixture means that everything is dissolved and dispersed evenly throughout the solution. So that means that in a homogeneous mixture, there are not distinct parts that we can pick out, right? Everything looks the same throughout the entire sample of that mixture, okay? Sometimes we have liquids that dissolve in one another, and sometimes we even have gas that can be dissolved in a liquid. Do you know, give me an example of a gas that's been dissolved in a liquid.
Water?
Liquid nitrogen.
No. Yeah, anything that's carbonated would technically be those CO2 molecules are dispersed evenly throughout that liquid, aren't they? For a while, until they get worked out, right? Until the pressure changes or the temperature changes enough and those gas particles escape. But to start, carbonated beverages have those CO2 molecules dissolved in the liquid, but they're dispersed evenly. So give me what on this slide? Okay. Properties of solutions, they are small particles that are evenly distributed, and in theoretical, a real solution, a true solution will not separate, right? An actual solution, we hope, does not separate. These are two vocabulary words that I think maybe you're familiar with, solvent and solute. Have you heard those? Okay, so the solvent is the thing that's doing the dissolving, and the solvent is the thing that is being dissolved. Okay, I'm going to demo making a solution here in like a few slides later. So I'll actually make a solution, because in chemistry, there's a specific process we go through to make solutions correctly. So I'm going to walk you through that in just a little bit. What do we typically use as the solvent? Water, right? Typically water is called the universal solvent, right? Because a lot of the things that we need to dissolve can dissolve in water. But does everything dissolve in water? What are some examples of things that don't dissolve in water? Oil, good. Grease. Butter, right? Any of those like things that have really fatty content don't dissolve in water, right? Oil-based things. What about salt? Does it dissolve in water? It does. What about sugar? Does it dissolve in water? It does. Okay, there is a whole set of compounds called salts. Okay, there's a whole set or a category of compounds called salts. And they typically contain a +1 cation and a -1 anion, or a +2 and a -2, right? That these group 1 and 2 and group 6 and 7, that when those combine in an ionic formula, typically are called salts. And a lot of those salts can be dissolved in water. Excuse me. So we use the term salt to describe sodium chloride, but in all reality, there's a huge category of compounds considered salts, and a lot of them dissolve in water. Okay. All right. So which one is our solute here?
No, it's Kool-Aid.
Solute. Typically the one in smaller amounts. Okay.
Is it like liquid IV solid?
What'd you say?
Is liquid IV a solid?
Yes.
We really want to get a bunch of it together. Make a big one.
All right. Typically the great substance in greater proportion is the solvent, and the substance in minor proportion is the solute. When water is the solvent, we call that an aqueous solution, right? Have you seen that where after a chemical we have an AQ in like a chemical formula? AQ means that that particular compound has been dissolved in water. And water is not affecting the reaction. So the reaction that we just did the other day, where we put sodium chloride and silver nitrate together, both of those were aqueous. Okay? Let me write out the chemical reaction for what we did the other day. We took NaCl aqueous, and we added it with silver nitrate. Oh, sorry, I don't need parentheses there. AgNO3 aqueous. And it formed what? AgCl and NaNO3. Okay, now, and in our products, was AgCl aqueous? No, it wasn't. What was it? It was a solid, right? That was the whole point, was that it became a solid, but NaNO3 was still aqueous, right? It was still dissolved in the water. So those ions didn't do anything, right? They stayed dissolved. So if you really looked at what products you had AgCl as a solid. And since this compound is aqueous, we really had sodium ions floating around and NO3 ions floating around, right? When something is aqueous and they've been dissolved, that means that those ions have separated, okay? And so in an aqueous solution, these were really our products: solid, silver chloride, sodium ions, and nitrate ions. Isn't that kind of interesting, right? That's what happened, right? When we put them in water, they all dissolved, and then when they started mushing together, the silver and the chloride combined to form a solid, and that's what the precipitate was. Okay, did somebody have a question? Okay, sorry. All right. I want to show you this little video here of the first part of the solution process requires energy. Name 2 ways to encourage the dissolving. So we said shaking, stirring, crushing the solute, all that kind of stuff. All of those things help us in the dissolving process. We could also add heat, couldn't we? I don't know if I put this slide in yours because we were just going to discuss it. I don't know if I did or not. Okay. So some of them I took out of your printed slides because if we were just going to discuss it, I didn't put them in there. Okay. Those are some ways we could do that. All right. This term, solubility. Have you heard that term before? Solubility, what's it mean?
Like how well it can dissolve.
Good. Okay. Solubility is basically a substance's ability to dissolve in water. How soluble, if something is soluble, that means it can dissolve in water. So solubility values, every compound has its own solubility range. And typically they're given in, this is how many grams of solute can dissolve in 100 grams of my solvent without it becoming overloaded, right? Or you dump so much in, it can't dissolve anymore. So solubility is a given value. Solubility can be affected by temperature, right? Objects can have greater solubility at a higher temperature, which means the hotter something is, I can put more of my solid in there and get it dissolved. And the colder something is, I can put less of it in there, right? That's typically the relationship you see there. But solubility is an object's ability to be dissolved in water. Okay? Here are some things that might affect a compound's solubility. We talked about temperature already. Temperature typically increases the solubility of solids and liquid. Okay, so solubility increases with the temperature increase. Right, and I think we've kind of talked about that before. If I want my substance to dissolve faster, I could heat it up, right? That would be a way I could do that. However, solubility between gases and liquids decreases with temperature. Have you seen an example of that? It doesn't have a lot of effect on solids and liquids and their ability to dissolve, but it does affect gases. When we have pressure with our carbonated beverages, for example, that actually is helpful for us, right? Typically, it keeps those gas particles engaged or in the liquid. But if you decrease your pressure, you're able to let it escape. So it just kind of depends on that situation and that range. But those are some things that can affect a compound's solubility. Okay. We talked a little bit about what it means to be a polar compound. You're going to hear this phrase, like dissolves like. Okay. You're going to hear that phrase often in your chemistry journey. And that just means that substances that are polar, like water, right? Polar is one side of my molecule has a positive side, one side of my molecule has a negative side. Substances that are polar dissolve really well in polar solvents because there's a constant pull of plus and minus, right? It works really well. The stronger the difference between the positive side and the negative side, the quicker it will dissolve because there's a really strong pull. The same is true for substances that are nonpolar. There's nonpolar dissolves nonpolar things. Okay, so the term like dissolves like means that polar solutes dissolve really well in polar liquids or polar solvents, and nonpolar dissolves really well in nonpolar. So that means a substance like butter or oil, those are nonpolar substances. That's why they don't dissolve in water, right? Water can't pick those things apart. Okay, but a nonpolar substance can help do that. Okay, let's get into our actual topic for today, which is how we can calculate the concentration of a solution. When I say concentration, what does that make you think of? Yep, how much of my stuff is in a certain amount of my liquid, right? That is what concentration is. And typically, the more concentrated something is, right? Let's think about it in terms of our Kool-Aid example, right? Concentrated might be I dump in 3 packets of Kool-Aid into 1 gallon of water instead of only 1 packet, right? Or whatever it might be. That means I'm really making it very concentrated. What would be the opposite? What happens if I do the opposite of that? Do you know what that's called? Diluting it. Good. If I dilute it, that means I'm adding more solvent than I should. Okay, so adding more solute than I should means I'm over concentrating it. Adding more solute or solvent would be diluting it. We're going to talk about that in the next couple of days. So, all right, this is how we measure concentration in a unit called molarity. So calculating molarity is the most common form of solution concentration. Okay, and we calculate molarity by taking moles of our solute over liters of our total solution. Okay, so capital M stands for molarity. Okay, that's the unit and it's the variable. Okay, so it's measured with a capital M, and that's the variable we use for it as well. So make sure your capital M's look like capital M's. This is not a capital M. Okay, make sure that we make, it's got to have mountains, okay, not hills. So molarity is capital M, and it's measured in moles per liter. Okay, so let's try this one here. It says a 4-gram sugar cube is dissolved in a teacup that holds 350 milliliters of water. What is the molarity of the solution? Okay, so I'm given the formula for sugar, and I'm given the mass, but do I put mass anywhere into my problem or my calculation? What do I need to put in? Moles. So the first thing I've got to do here is convert 4 grams of sugar, C6H22O11. I've got to convert that from grams to moles. Okay, so let's go ahead and find molar mass.
That's the fat one. Pretty big. 270.
Okay, molar mass, did we come out at about 270 grams? Okay, and so my number of moles here is going to be really small, isn't it? Right, so I'm going to take 4 divided by that. Okay, so we're at that many moles of sugar. And I need to take that over liters of the whole solution. Okay, it says this teacup holds this much. So I'm going to assume that we're using all of that, right? That we're going to make that much solution. We have to be kind of careful here in our problems to make sure it's not saying we're adding this much water to our solution or whatever. We need to make sure that the amount of liters that we use is of our entire solution. So it's including the volume of whatever solute you dumped in, right? Because even this 4-gram sugar cube, when we put it in there, is going to raise the volume a little bit. Okay, so by using that 350, we know we're accounting for the volume of that solid as well. Okay, so I'm going to take that many moles over. I need liters, but it's given to me in milliliters. How do I convert that? Not times 1,000. Divide by 1,000. Right, I should have a smaller number of liters than milliliters. And so I get a molarity of 0.042. And then we just put a capital M. That's our unit that goes on the end there. Okay, and the way I would read that is I would say I have a concentration of 0.042 molar. Okay, 0.042 molar. So molar is the unit there. Okay, that would be my concentration. Are those numbers similar to what you had? 0.042. Okay, so if I said, what's my concentration of solution? I would say it's 0.042 molar. Okay, or it has a molarity of 0.042. What's the concentration in molarity of a solution formed by mixing 10 grams of, what's that molecule called? Sulfuric acid. Sulfuric acid. Hydrogen comes first, which means it is an acid. Okay. This says mixing 10 grams of water with mixing 10 grams of sulfuric acid with enough water to make 100 mils of solution. So first thing I've got to do is convert grams to moles. So grams to moles. Okay, is that what we had for our moles? And then do I divide that by 100? By 0.1 liters, right? This needs to be divided. So our liters always has to be smaller than our amount of milliliters, okay? So 0.102 divided by 0.1 gives me 1.02, and how do I say it? 1.02 molar. 1.02 molar. Good. 1.02 molar.
Do we not need to say like what it is?
No, you don't have to necessarily put the H2SO4 at the end. I won't take off for it, but it's not something we have to have. Okay. Why don't you try the next one on your own? How many liters of a 3.4 molar isopropanol solution can be made with 78 grams of isopropanol? So this time you're solving for your volume. How much of your solution can you make? Okay, I'll give you about a minute head start, then I'll put it up here. All right. Last one here. How many grams of potassium phosphate would be needed to make a 1.32 molar solution in a container that holds 4.2 liters. So it's asking me for grams of potassium phosphate. Okay. The first thing I think I need to do is I need to know what's the formula for potassium phosphate. I'm going to need it eventually. I don't necessarily have to have it first, but let's go ahead and find it first. So potassium phosphate, do we got an idea of what it might be? K3PO4. Phosphate is a -3 and potassium is a +1. So K3PO4. I don't necessarily have to have that right away, but I'm going to need it, so I'm going to put it up there. I've got my molarity and my volume, my liters. So I'll say 1.32 molar equals moles over 4.2 liters. Now what's the math I have to do? Now I'm just multiplying because I just need moles by itself. So now I'm just getting rid of this. And whatever I do on the right-hand side, I have to do on the left-hand side. Right? Are we clear on that algebra? Okay. So I'm just going to take that multiplied through it because this time the thing I'm looking for is already in the numerator. Right? So I'm not having to move it out of there. So 1.32 times 4.2 gives me 5.54 moles. Is that where my problem gets to stop? No, I have to go ahead and take it all the way to grams because that's what it asked me for. So that's why I needed to know my formula, because I will need to know molar mass. Right? If it just asked me for moles of potassium phosphate, would I really have needed to know the formula? No. All right, if it just asked me for moles, I wouldn't have even needed the formula. Okay, but it asked me for grams. So 1 mole is equal to 212. Is that what you said?
Yeah.
Okay. And so that means, oh, I need a lot. 1,174.5 grams. K3PO4. That's a lot of grams. Is that right?
Yeah,
I got 1,119.
I got around it.
Did you accidentally push in 5.45 maybe?
No, I have 5.
No? Okay.
I got 28.
How would I actually make a solution of 100 mils of 0.25 molar salt water? Okay. This is going to be a process that I want you to have a familiarity with. So I'm going to write down some steps for making the solution. The first thing we have to do when we make a solution is we have to use a volumetric flask. We use what's called a volumetric flask to make a solution. And a volumetric flask is a type of glassware that we haven't used yet, but it looks just like this. Okay, a volumetric flask looks like this. It only has one marking on it. Okay, there's only one single marking on it, which means this particular glassware can only be used to measure 100 milliliters, and that's it. I can't make 50 milliliters of solution in this volumetric flask because I only have one marking. So when you're making a solution, if you overshoot your marking, you have to do it again. There's no, you don't get the choice because that's it, right? You're one and done. So we use a volumetric flask because it's measured so precisely to 100 milliliters. Okay? So you're going to have to just write these steps in as we go. I'm probably not going to write it up on the board, but so we've got, actually, I will. We've got to make that 0.25 molar solution. So I need to figure out how many grams of salt am I going to use in my 100 ml flask. Let's go off to the side and calculate that as well. Okay, so 0.25 molar equals moles over 0.1 liters. Okay, so let's figure out how much salt am I going to need to use here. Okay, 0.25 times 0.1. Okay, 0.025 moles of NaCl. And I'm going to convert that to grams. Okay. So that means I need about 1.463 grams of NaCl, roughly. Okay. to make my solution, I need this many grams. Okay? So we're going to pick out a volumetric flask. We're going to fill part way with water. Okay? Not all the way, but part of the way with water. Okay, I'm going to then add my solute and mix. Okay, I'm making my steps pretty simple here, but okay, so I just so happen to have 1.463 grams of salt here. I've got my water level part way. Why do you think I don't want to fill it all the way? Why can't I fill it all the way up first? Right, the salt that I'm adding has volume. Not a lot, but it has volume, and so it would raise me over my mark. So that's why I don't want that. What's the other reason I probably don't want to add it first? I don't want to fill it first. Yeah, it's going to make it really hard to stir. There's not a lot of room in there. Okay, so we fill it part way. We add our solute, right? I would rinse it if I was doing it correctly here. So I'm going to rinse it into there. Okay? If I really wanted to get it all out, I would make sure I rinse it in. Okay? And then from there, we're going to mix. And so if I was using something more intense than salt water, I put the lid on. But for right now, I can use my thumb. Okay? And when we mix, we just go over and back. Right? That's really all we have to do. Over and back. Okay? Until we feel like it's all the way dissolved. That gives us, right, by not feeling it, it gives us some room to let that move around. Right? We could shake if we needed to, whatever we're going to do. But we're going to do that, right? And we're going to take our thumb off. And now I've got to fill it really, really carefully to the line. Okay, so if I was closer to a sink, I might fill a little bit more. But I've got to go really carefully to make sure that the meniscus, you remember what the meniscus is? The curve, right? We want the bottom of the meniscus on that line. Okay, and so we're going to fill it very carefully at the end. Okay, you might even say that at the end we fill it drop by drop. Okay, so we're getting close, 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 close. So I'll take a break, see kind of where I'm at. Okay, if I was not 9 months pregnant, I would get a high level, but I'm just going to do it like this. Okay, so we're going to fill it close to that line, and then we're going to kind of go drop by drop. Okay, so that means we're going a little bit at a time. Okay, I think that's pretty close. Okay, so that's what we're looking for. And if I would have overshot to here, I would have to throw it out and start over. Right, because then my concentration is not what I said it was. Right, if my concentration is not what I say it was, then I can't do my experiment with what I thought it was. Right, but that's pretty good. Okay, so that's our key to making our solution is volumetric flask. We don't make solutions in graduated cylinders, anything like that. Volumetric flask, fill part way, add our solute, mix, and then you can say add water drop by drop. That could be our last step here, okay? So when I ask you how to make a solution, you're going to write out those steps, right? You don't need to write out the math you did, but you might say, in this case, I might say add 1.463 grams of NaCl, right? I might be specific in how I made that solution, but I'm not going to walk you through the math of how to find that. Yeah.
Why don't you put the salt in before the water?
You could put the solute in first if you want. It makes no difference. Yeah. We just want to not have it filled all the way. Okay? Then at the end we want to say drop by drop to the line.